Let's continue the discussion from last time. Any questions from the previous class? Okay, so let's do a quick recap. In the last class, we looked at these class of Chernoff bounds, right? So we were looking at multiple tail bounds on general random variables. We first saw Markov's inequality and then we saw Chebyshev's inequality. But both of these only gave us polynomially decaying bounds on the probability of deviation from the mean, right? So remember that our goal is to somehow try to derive the tightest possible bounds on the following quantity, which is the probability that x minus the mean deviates from by an amount of delta. And one class of bounds that we saw was this Chernoff bound, which says that if x is a random variable for which all the moments exist, then the probability that x deviates from the mean by an amount of delta is upper bounded by the moment generating function divided by e raised to t times mu plus delta. And this holds for every value of t, right? So since it holds for every value of t, it also holds for the t for which the right hand side is minimum, right? That would give us the best possible bound. Now at times it's possible to minimize the right hand side exactly, sometimes it's not. So in that case, even if we can evaluate this at one particular t, it still gives us something, a valid bound, right? And that is what we will do for most random variables. Now we saw a couple of examples in the last class, particularly Bernoulli random variables and Gaussian random variables. Right? For the Gaussian random variable, we derived an exact bound for the right hand side. We minimized the moment generating function divided by e raised to t times mu plus delta, and saw that the probability that x minus mu is greater than or equal to delta is upper bounded by e raised to minus delta square divided by 2 sigma square. And this is in fact a pretty good bound for Gaussians. You can't really improve over this except for perhaps improving the constants. Even if you try to exactly evaluate the integral, you'll be off by at most a constant. So this is not too bad, right? And then we use this to, at least the bound for Bernoulli random variables, to say something about random graphs, in particular what is the degree distribution of the random graph. And we saw that for an Erdős-Renyi graph, as long as p grows sufficiently fast with n, all the degrees are very close to n times p with high probability, right? So the degree distribution is almost uniform in some sense. In today's class, we'll see another application, particularly using concentration for Gaussian random variables. So in the last class, we derived the following fact, that if x is a Gaussian random variable with mean mu and variance sigma square, then the probability that x deviates from its mean by an amount delta is upper bounded by e to the minus 2 times e to the minus delta square by 2 sigma square. Right? So we won't exactly use this, but in fact we'll use the Chernoff bound for not Gaussian random variables, but rather chi-squared random variables. So this takes me back to one of the examples that we had in the very first class, which is the following problem. So suppose we want to communicate across a noisy channel. Right? So what is a channel? A channel is simply, you can think of it as a black box. So if you give as input a vector in Rn, then the output is also a vector in Rn, and it is given by x plus z, where z has independent and identically distributed components, which are all Gaussian with zero mean and variance sigma square. All right, this is called the additive white Gaussian noise channel. Okay, our goal is to be able to somehow communicate reliably across this particular channel. So let me say what I mean by that. So the end goal is to transmit a message across this channel such that the message can be recovered with high probability. Right? The probability that you make a mistake in decoding the correct message should be something that is really, really small. So suppose I have a message in particular. I'll assume that there are m possible messages and you want to transmit one of those m possible messages. This m is decided beforehand, and so is n, the number of times you're using this channel or the size of this particular vector. You can think of n to be a representation of how long you're transmitting, what is the duration of transmission. And m is, in some sense, the number of useful bits, the number of information bits that you transmit across the channel. In fact, it's not m, but rather log m. So suppose you want to transmit k bits, that corresponds to 2 to the k possible messages. And ideally, you want to design some kind of a scheme which allows you to transmit a large number of information bits by using the channel as few times as possible. So main goal is to have m to be as large as possible for a given n, or for a given m you want n to be as small as possible. Right? Is this high level description clear? Okay. Now you don't want to be transmitting the message as it is. That's not particularly helpful. But instead you want to encode the message into this vector which I call the code word. Right? So basically what the encoder does is, for each message it identifies one particular vector to transmit, and this is again designed beforehand. So given any message, so someone tells you that you want to transmit this particular message, you think of the messages being one of m possible files. Or if you want to transmit, let's say, k bits, then there are 2 to the k possible messages and you want to transmit one of these. Any k bit string is one particular message. Now for each k bit string or each message, there is some particular code word that you are going to transmit, and this is decided beforehand. Now given that this is, of course, what is received is not exactly the transmitted code word, but some corrupted version of this code word. Right? It's code word plus noise. So we need to design a decoder which gives us an estimate of the message. So one way to think about this is, you have code words x of 1, x of 2 up to x of m. Right? For each message you have a different code word that is somehow designed. Your goal is to design this. So these are all the code words, and the set of code words is what I call the code book. Okay. So this, you transmit one code word from this particular code book. This is designed beforehand. The decoder also knows the code book, but it doesn't know which exact code word was transmitted. Okay. So So both the encoder and the decoder know the code book. The encoder also knows the message to be transmitted. All right, does this make sense? Great. So what the receiver gets is X plus some noise, and from Y you want to be able to find out which of these code words was transmitted. So we're dealing with Euclidean space. What is a natural decoder that you can think of? Just give a guess. What would you do? Okay, minimum distance, right? That's one particular decoder. So one choice of decoder is basically output the argmin minimizing the distance is the same as minimizing the squared distance. So that is one possible decoder. It's called the minimum distance decoder. And if you've taken a course in digital communications, this also happens to be the maximum likelihood decoder. All right. So right now what we'll do is we'll try to analyze the performance of this minimum distance decoder. Okay. We'll first try to analyze the performance of a minimum distance decoder, and then we'll try to think of how we can possibly come up with code design. Right? What is a good way of, how do you decide whether a code is good or not? Okay. So is the setup clear? Okay. So in addition to this, the code book sometimes also has to satisfy an additional constraint like a power constraint. So we'll also impose that. So what we want is that the 2 norm is less than or equal to n times p for some constant p. It is the same as saying 1 over n summation j equal to 1 to n xj of I squared is less than or equal to p, where xj of I denotes the jth component of the ith code word. Okay, and this has to happen for all I. All code words should satisfy this constraint. Now this is what happens This is part of the codebook design. How do you design a good encoder? But let's first try to analyze the decoder. Suppose somebody gives you a codebook. Can I derive a bound on the probability of error for this particular code? May not be exactly the probability of error that is achieved by that, but even if I can get a decent enough bound, that's good enough for me, right? So let's try to do that. So right now we've fixed the code book. Alright, and for this we want to know what is the probability that this particular decoder, the minimum distance decoder, makes an error. Which one? Can you speak up? Can you speak a little louder? P is what I call the power constraint, is some number. It's part of the system design. This is the total amount of power that you're allowed to use. It is the same for all the code words. Right? So, I mean, it should be less than or equal to P. So for some code words, this 2 norm squared could be less than n times P, but in any case, it should not exceed P. Okay. So the geometric interpretation of this is, if you think of these code words as points in n-dimensional space, then what this power constraint basically says is that all of these should lie within a ball of radius square root n times P. Right, so let's make, maybe that's a useful point to make note of. So really the geometric way of thinking about this is you have all of these code words which have to lie within this ball of radius square root n times P. And so on. Okay. Great. Okay, so what would be the probability of error of the minimum distance decoder? Suppose that I transmitted message I. What is the probability that it is received in error? So let's look at what is the probability that the estimate is not equal to I, given that the actual transmitted message is equal to I. let's not worry about how to compute this exactly, but let's try to write this in terms of events. What is the event that we're interested in understanding? So when do you decode to something other than I? Correct. So the received vector is closer to some other vector than the actual transmitted vector. So I can write this as, this is equal to the probability that the distance between y and say the jth code word is less than or equal to the distance between the received vector and the ith code word, given that the message transmitted is equal to I. Sorry, yeah, so this is for some j not equal to I. And exactly as you pointed out, this is essentially a union of events. It's a union of how many events? M minus 1 possible events. So it can be, it's closer to x of, suppose that the transmitted vector is x of 1, the transmitted message is 1, then it's closer to x of 2 or x of 3 or x of 4 up to x of m. So this is equal to the probability of the union of a bunch of events Okay. All right. So as I said, we are only interested in getting an upper bound on the probability of error. So how do we simplify? What's the first step we can think of in simplifying this? I'm sorry? Can you speak up? Why we are not considering y? You mean to say why this is a union of over all j not equal to I? Well, that's because when does an error occur? So in this case, the jth code word is closer to y than the ith code word. If the ith code word is the closest code word, then it's not in error, right? So this is an event, right? Only the encoder knows that the transmitted message was I, right? The decoder doesn't know which message was transmitted. We are not sure that the message is I or no, you don't know. So then so this is assuming that I was transmitted. In fact, what we want to see is, okay, for any message transmitted message, we want such a bound. Correct. That is true. Yes. So this is not the total probability of error, because you also need to average over the messages as well. Right now, I'm trying to look at a more basic quantity, which is the probability of error given that ith message was transmitted. The overall probability of error is exactly as you pointed out. It is, you have to average this over all possible I as well. Okay. All right, so a favorite way of bounding this is just use the union bound, because we want to simplify things. And in general, whenever you have a complicated union of events, you try to break it down as a sum of probabilities, sum of bad probabilities. So this is less than or equal to summation j equal to 1 to m, j not equal to I of probability that y minus x of j squared is less than or equal to norm y minus x of I square, given that the transmitted message was equal to I. So now this probability only depends on a pair of code words, x of I and x of j, nothing else. It doesn't depend on the rest of the code book. And that in particular makes it much easier to handle. Right? So the overall probability of error this is in fact equal to, assume that all of the messages are equally likely to be transmitted, 1 over m summation I equal to 1 to m, probability that the estimate of the message is not equal to I, given that the actual message that was transmitted is equal to I. All right, great. So now we want to analyze this particular quantity. So this is just equal, this is less than or equal to 1 over m summation I equal to 1 to m summation j equal to 1 to m, but j is not equal to I, of the probability that the distance between y and x of j is less than or equal to distance between y and x of I. Right? So, I mean, this is algebra. So let's try to think about this geometrically as well, because that kind of helps. So again, I'm representing this in two-dimensional space, but all of this is happening in a much higher dimensional space. So you have a bunch of these code words all in Rn. Maybe let me let's say that I have 4 possible messages that can be transmitted, and for each of these I have a different code word, right? And let's say that the ith code, the transmitted code word was actually this one, right? This particular code word was transmitted. Now, what does the decoder do? It finds the closest possible message. Right. So, in fact, if let's say, I mean, this is only drawn approximately. So, let's say that this region is the set of all points in space which are closer to this code word than any other code word. Similarly, this region is the set of all points in space which are closer to this particular code word than any of the other code words, and so on. So, the actual probability of error is the probability that you transmit something, but you receive something which is, let's say you transmitted this code word, but you received something in one of these other regions. Right? That's the true probability of error, given that this particular code word was transmitted. That's not necessarily, because the received vector could lie anywhere in space. Correct. The transmitted, but you know the code book beforehand anyway. Right? So the power constraint is what it is. It's a constraint. Of course, you could think of designing more intelligent code books or decoders, but for now it doesn't really matter. Right? For now, you don't have to worry about the power constraint at all in analyzing the probability of error. Okay. So essentially, if the decoder, if the received vector is anywhere in these regions, then that corresponds to an error. Right? But now what we are trying to do is essentially trying to derive a bound on the probability of error. So you pick a particular pair, right? For example, let's say this particular code word and say this particular code word. Right? This is my I. This is my I, and this is my J. Right? Now, if you look at the set of all points, if you just look at this particular pair, then, and you look at this particular event, that is, what is the probability that the received vector lies closer to J than to I? Right? So that corresponds to the following, potentially the following event. Right? So if you just, assuming that these were the only two code words in the universe, you make an error, that is, you decode to J instead of I if the received vector lies anywhere above this particular line or above this hyperplane. Correct? Now, again, when you look at, say, this particular pair, this is I and this is J, then you make an error if, say, you're anywhere to the right of this particular hyperplane. Okay? And now you can see that this is indeed a bound. Because when you just look at these three code words, for the first pair, the probability that you make an error, that is this particular probability, was equal to the probability that the received vector is anywhere above this particular pink line. Whereas now if I consider a different J, say this is my J prime. This is my J prime. Then the probability of error for this pair I and J prime is the probability that the received vector lies to the right of this orange hyperplane. So now this particular region is being counted twice. So the probability of this plus the probability that it lies anywhere over here. So it's clearly an upper bound and potentially a very loose upper bound. That's something to keep in mind. Okay, but nevertheless it just makes our life simpler because now we only need to consider pairs of code words and nothing else. So in fact all that matters is just this particular pair, and that will simplify even further. Now what is y equal to? Assuming that the message, the transmitted message was equal to I, what is y equal to? It's equal to x of I plus c, right? So this is equal to x of I plus z. So let's rewrite this particular event, that is y minus x of j whole square is less than or equal to y minus x of I the whole square. So y is simply x of I plus z. So this is x of I plus z minus x of j squared less than or equal to x of I plus z minus x of I squared. This just cancels out. Right? I'll write this a little more carefully. I'll write this as x of I minus x of j plus z square less than or equal to norm z square. Right? Right? So what happens when I expand the left hand side? Yep. Okay. So x of I, x of j transpose times z plus norm z square is less than or equal to norm z square. I'm sorry. Where? So this is x of I minus x of j the whole square plus norm z square.
Establish the second term of norm.
Okay, sure. Yes, right. So norm z square gets cancelled out, and as long as this quantity is less than or equal to 0, then not, right. So all of this essentially boils down to finding, now this quantity doesn't depend on z, it's a deterministic quantity, it depends only on the pair of code words x of I and x of j. In fact, it only depends on the distance between x of I and x of j, nothing else. Whereas this depends on x of I and x of j in a slightly more complicated way, right? Great. So now, again, we'll make another simplification. Instead of looking at this itself, let's again think of this geometrically, right? So what we want to understand is, when can we say, so instead of analyzing the exact probability of error for this particular code book, when can we guarantee that I and j will not be in error? So when can you say that when you transmit I, you will not decode to j? Can we come up with sort of a sufficient condition? Okay. So to do that, let's first try to analyze. So you see, all of this ultimately depends on just the noise vector z. If we are able to understand how the noise vector behaves in high dimensions, then we'll have a better handle on this particular probability of error, right? So in particular, so let's see, for large enough n, where does z typically lie? Okay, that's what we'll try to analyze. Okay. So in particular, let's see what can we say about not just z but also the norm of z. So let me try to give some intuition as to why I'm interested in the norm of z. Suppose I know that, now I'm interested in just this pair I and j, right? The geometric view that you need to have is that you have I, and you have this is your x of I, and what you receive is x of I plus z. This is your x of I plus z. As long as x of I plus z is below this particular pink hyperplane, you're not in error. If it is above the pink hyperplane, then you are in error, right? So ultimately it depends on how much z shifts x of I. and by how much, at least visually, how much can it shift x of I so that it's not definitely not in error? Half of the distance between x of I and x of j, right? So if the norm of z is less than half of the distance between x of I and x of j, then it won't be in error, right? That's, you're safe. But again, it is not necessary that it should be less than half of the norm. So for example, you could be really far away from x of I, but in maybe the completely opposite direction. Even then you are not in error, right? But definitely, if the norm of z is less than half of the minimum distance, less than half of the distance between x of I and x of j, then you will not be in error. Let's find the probability that that happens. So let's look at the norm of z. So norm of z square, it's just equal to summation I equal to 1 to n zi square. What do we know about z? Yeah, it's Gaussian with zero mean and variance sigma square, right? So this is a sum. What can you say about z square? Z is Gaussian, right? So what can you say about z square? It's chi-square distribution with how many degrees of freedom? The sum will have n degrees of freedom. So each one is going to have, each individual component is going to have just 1 degree of freedom. So z square or zi square is chi-square with 1 degree of freedom, essentially. So this is, I think, 1 over gamma half root 2 e to the minus. So this would be the density of zi square, and the moment generating function of zi square is equal to 1 over 1 minus two t whole to the power half for t less than half. Right. Now, in fact, I could have analyzed this as a chi-squared random variable with n degrees of freedom, but that's going to be more complicated for me to handle. In fact, I'd prefer to use this particular tail bound because it also allows us to generalize what we've already seen. If you can say something about one random variable for n random variables, it's a simple enough bound that we can derive, right? So what is the expected true norm square? So again, to simplify, let's assume that each zi is, assume that the variance is equal to 1. Okay, that will just simplify calculations, but what is the expectation of, what is the expected 2 norm square? Right, so that's equal to n because each zi square, so expected value of zi square essentially just corresponds to the second moment of zi, and it's Gaussian with 0 mean and variance 1, so this expectation of zi square is equal to 1. Sum of expectation zi square is equal to n. Right? Okay. So far, based on what we've seen so far, what do you expect that we'll be able to say about the norm of zi square or the norm of z square? Yeah, it should be very close to n, right? So in fact, let's try to find what is the probability that norm z square is greater than or equal to n into say 1 plus epsilon. Right? What does the Chernoff bound tell us? I can write this as, this is the same as probability that 1 over n summation I equal to 1 to n zi square minus 1 is greater than or equal to epsilon. So it's again a sum of or an average of IID random variables, each random variable being chi-square. Okay, so the moment generating function of zi square yeah by e to the power t into 1 plus epsilon. Does it depend on n? How does it depend on n? By n? Correct, summation, but well, it will be the average, or if you want to take the summation, then there would be summation I equal to 1 to n zi square minus n greater than or equal to n times epsilon. So what is the moment generating function of the sum of independent random variables? Whole to the power of n. It's just going to be this whole to the power of n. Right? Okay. So what is this particular quantity going to be? In fact, this is less than or equal to infimum overall t less than half of this.
What will be greater than
Can you speak up?
what will be greater than we didn't define it.
So the moment generating function is defined only for t greater than t less than half. If t is greater than half, then the moment generating function is an integral. The integral is defined only when t is less than. The function is not defined. Right? So what does this give you? This I can write this as e to the minus t into 1 plus epsilon plus what is this mgf equal to? So it's 1 over square root of 1 minus 2t, right? So which is the same as e to the power log of 1 over square root of 1 minus 2t, or minus log square root of 1 minus 2t right? Okay, so let's try to minimize this particular exponent, or yeah, let's try to minimize this particular exponent over here. Let me call this psi of t. What kind of a function is psi of t? We want to maximize this or minimize this? So this whole quantity over here, you want to maximize the negative of this exponent or minimize the exponent itself. So what do you get when you minimize this? So 1 minus epsilon is equal to 1 by 1 minus 2t, or What is t equal to? Sorry, 1 plus epsilon. So what is t equal to? One by two into why do you get epsilon by 1 plus epsilon? So 1 by 2 into epsilon by 1 plus epsilon. Okay. So what happens to this particular quantity here? What is the Chernoff bound equal to? Right? So the main point here is that the dominant, or this, I can also write this as 1 over one plus epsilon times e raised to minus epsilon over 2. Okay. Okay, so if I plug this back in, I get the probability that 2 norm square of z is greater than or equal to 1 plus epsilon times n is less than or equal to 1 over or square root 1 plus epsilon e raised to minus n epsilon, right? Now if epsilon is sufficiently small and n is sufficiently large, then really the dominant factor is e raised to minus n times epsilon. Right? So this behaves roughly like e raised to some constant times n epsilon. Now, in fact, you can also prove a similar bound on the following quantity, what is the probability that norm z square is less than or equal to 1 minus epsilon times n? This will also be less than or equal to e raised to minus constant times n epsilon. Now, one thing to note is that this holds for any epsilon and any n. Right? There's some universal constant c for which this happens. Right? So what does this tell us geometrically? As n becomes larger and larger, with very high probability, the 2 norm of z is going to be very close to square root of n. For the 2 norm square, it is very close to n. So if you think of, again, in high dimensions, if you think of what is happening, if you think of a ball of radius 1, right, or sorry, a ball of radius square root of n, in general is going to be square root of n times sigma square. A lot of the probability is in fact concentrated within a thin shell around this particular thing. So there's a band. Let me so you can think of a ball so this is a ball of radius square root n sigma square, right? The inner ball is a ball of radius square root n sigma square into 1 minus epsilon, and the outer ball has radius square root n sigma square into 1 plus epsilon. What do these two statements combined tell us? What is the probability that z lies inside the inner ball or outside the outer ball? Yeah, so it's something that decays exponentially in n times epsilon, right? So the probability that z lies inside the inner ball or outside this is 2 times e raised to minus some constant times n times epsilon. So what this says is that much of the probability is in fact contained in this thin shell of thickness epsilon. In fact, you can make the epsilon to be dependent on n. Right? So even if I choose, let's say, epsilon to be 1 over square root of n, or even 1 over some polynomial in log n, that still works. I can still have the right hand side vanishing as n tends to infinity. Right? So even if the thickness of this shell is just 1 over some polynomial in log n, much of the probability still lies inside this shell. Right? And that's a surprising feature of what happens in high dimensions. If you think about a two-dimensional ball, it's a circle, or a three-dimensional ball, where is much of the volume concentrated? It's everywhere inside the ball, right? It's kind of uniform inside the circle. But that is not necessarily what happens in higher dimensions. Right? So this is a Gaussian. If you think of, let's say, a one-dimensional Gaussian, what happens? If you think about it, just a one-dimensional Gaussian, much of the probability is in fact in this particular region. In fact, the probability is more concentrated close to zero. That's what you would intuitively assume. You look at a two-dimensional Gaussian, again the density is sort of radially decreasing. And that happens in higher dimensions as well. The density is still radially decreasing. As you go farther away from the origin, the value of the density function in fact decreases. But this particular statement is rather surprising because it says that most of the probability is not concentrated very close to the origin. It's in fact concentrated away from the origin. It's concentrated in a very thin shell. And one of the reasons why this particular phenomena happens is really because if you think of an n-dimensional ball for really large n, then much of the volume of this ball is not concentrated close to the origin. It's concentrated very close to the surface. So the volume of an n-dimensional ball is exactly given by pi raised to n by 2 divided by gamma n by 2 plus 1 times r to the n, where r is the radius of the ball. And if you just apply Stirling's approximation, you can in fact prove that that much of the volume is very close to r. It's very close to the surface. So that is that's a rather counterintuitive phenomena that happens in high dimensions, which does not happen in lower dimensional objects. Right? Okay, so now coming back to our problem of communication. What does this tell us? It says that if n is sufficiently large, then with very high probability, the norm of the noise vector is going to be at most n times sigma square or square root n sigma square times 1 plus epsilon. It's going to be very close to that. So if the distance between x of I and x of j is greater than 2 times square root n sigma square, then it's fine. The probability that you're in error is like really, really small. So suppose what we've shown is that the probability that norm z square is greater than or equal to n sigma square into 1 plus epsilon is less than or equal to whatever e raised to minus some constant times n epsilon. The constant can depend on sigma square, but that doesn't really matter. For us, our only interest is in how this depends on n. So if I have x of I, if the distance between x of I and x of j is greater than 2n sigma square into 1 plus epsilon, then the probability that you mistake I for j, or probability that their estimate is equal to j, given that the actual message transmitted was equal to I, is upper bounded by e raised to minus some constant times n times epsilon. In fact, this is a very, very loose upper bound, but doesn't matter. That's good enough. Okay. So, and this holds true for any I comma j for which the minimum distance is greater than 2 times n sigma square into 1 plus epsilon. Right? So now what can I say about the probability of error? It's less than or equal to 1 over m summation I equal to 1 to m summation j not equal to I of the probability that you estimate that the decoder outputs j, given that the transmitter wanted to transmit I. So this is at most j not equal to I, e raised to minus constant times n times epsilon. If I sum over all possible j not equal to I just get m minus 1 times e raised to minus constant times n times epsilon. Right? Of course, this is assuming the distance between any two pair of code words is at least square root n times sigma square. This is again only an upper bound. So as long as we are able to construct a code for which the minimum distance is at least n times sigma square or square root n times sigma square, we are done. We know that the probability of error is guaranteed to be small. Right? And in fact, these are the kind of calculations that you do in communications and information theory. Whenever you're dealing with communication over noisy channels, the first step is to always get an upper bound on this pairwise probability of error. And ideally, you make use of something like some sort of a concentration inequality to show that this is exponentially decaying in n, so that everything else, just using the union bound, you get something that's good enough. This is only to give you a flavor. There are other sort of tricks that you can play to get even tighter upper bounds, but the very high level idea is always the same. So just to very quickly recap, so today we saw an application of a tail bound for chi-squared random variables. Right? And another very useful property that we saw was this phenomena of what happens in high dimensions. So if you take a high dimensional Gaussian random vector, then most of the probability lies in a very thin shell that is far away from the origin. And the reason why this happens is that in high dimensions, most of the volume of an n-dimensional ball of a given radius actually is very close to its surface and not close to the origin. Alright, so that's where most of the probability is concentrated. Okay, so let's stop here. Any questions? Okay.